Thank you very much. I would like to thank the organizers for setting up this fantastic meeting. Particular thanks to Romain, who took care of absolutely everything, including ordre de mission. It's amazing. I don't know how he does it. Yes, so I'm going to discuss light-emitting metasurfaces. So the complex medium is metasurfaces. It's order medium. What is random is the sources. So we are going to discuss how to tailor spontaneous emission. And well, let me show you the goal. That's a typical projector. And you have an incoherent source here. It's not a laser. But then you need to shape your light. You might want to collimate the beam. You might want to control the spectrum, the polarization. And when you do that, you keep adding things. So you end up with something which is bulky. And every time you add a component, it does not transmit everything, so you lose light, so you decrease your efficiency, and you increase the cost of production and the total mass of the device. And the question is, could you replace by that, where you would have a simple surface whose thickness would be the substrate thickness, say a fraction of millimeter, plus 1 micron or a few hundreds of nanometers of active surface, that you do all the job and took care of everything. So that's the goal. So in particular, one of the challenges is to have the emission of a directional beam out of incoherent sources. And then to do that, we need to play a number of tricks from nanophotonics. So I will start with a crash course on nanophotonics tricks and the toolbox. I will give you a few highlights on some of the tools we have developed in nanophotonics to do that. So this will be, you can have much more information on this book that has been published recently in Oxford, which was written with my colleagues, that it's impossible to read here. It's Henri Benisti, my name, and here Philippe Lalanne. So we are 3 colleagues in, and actually the real book is almost like that. I don't know how they managed to do that. So we cover all areas of nanophotonics, which is a kind of, the word nanophotonics really started 25 years ago, and it's the merge of people coming from semiconductors, from adaptive optics, from diffractive optics, and from super resolution microscopy. So, and chemists who developed the devices, you will see that we synthesize colloidal quantum dots. That was a chemistry Nobel Prize last year. So it's really an interdisciplinary discipline, and there was a need to kind of group all this knowledge. Okay, so for what is of interest today, which is emission of light, what is very specific in nanophotonics is the fact that the volume can be very small. So the interaction between matter and light is given by this interaction Hamiltonian, where this is the dipole moment and this is the electric field. Now, the electric field is the electric field of the mode that you want to excite. In the crash course on quantum optics yesterday, you've seen this term, which is in prefactor of your creation and annihilation operators. And this V here does not play any role in quantum optics. For instance, when you use that and you compute using quantum optics, you have to. The rate of spontaneous emission, at the end of the day, you get a rate of spontaneous emission which is independent of the volume. And it's the rate of emission of your atom or your molecule in vacuum. And for many years, people thought that that was a characteristic of an atom. This is not true. It depends on the environment of the atom. If you take this atom or that molecule and you put it close to a mirror, by close I mean within the wavelength or so, then you have modifications of the rate of emission. That means that you can modify how you extract light by modifying the electromagnetic environment of your sources. And that's what I'm going to do in this talk. What you can see from this is that if now you realize that, yes, indeed, your mode depends on the volume, then you see that the interaction between light and matter can be enhanced if this electric field is larger, and this you can do by reducing the volume. So if we can now develop a volume that is extremely small, then the field becomes extremely large. It is possible to do nonlinear optics without lasers with 2, 3, 4 photons, because the electric field becomes extremely large if your photon is inside a volume which is much smaller than the wavelength. So that's what nanophotonics is. You confine the light, and by confining the light with a single or 2 photons, you have a huge electric field. So that's one of the key ideas. So the question is, how do you confine light? And if you think in terms of cavity, then you know that you take, it's a microwave oven, you have a metallic mirror, so a Fabry-Perot, and then you have a mode, the smallest mode has lambda over 2, and you cannot go below that. So it's the end of the game. So what I told you is nonsense, because we don't know how to do a smaller cavity, so we cannot reduce the volume. But this is because you are thinking in terms of waves in vacuum. If now you introduce an additional degree of freedom, which is charges, matter, then it is possible to localize the electromagnetic field. It's no longer a pure photon in vacuum. It becomes a coupled electromagnetic mode coupled to matter. So it's called a polariton. But that polariton can be confined to extremely sub-wavelength volumes. And by doing that, you achieve this dream of having a huge electric field with a tiny mode. One of the key ideas or key tricks to do that is to use surface plasmons. So that's a particular example of a system that enables you to confine light. So I'm going to tell you briefly what is a surface plasmon. There are actually 2 classes of surface plasmon. One is between an interface between a dielectric, say vacuum, and a metal, say gold. And you have such a wave which decays exponentially away from the interface and propagates along the interface. We also call surface plasmon, we call them localized surface plasmon if you have a nanoparticle. So imagine that you have a spheric sphere of 5, 10 nanometers of diameter in gold, silver, whatever. And you have an excitation. So you see I've drawn here positive and negative charges. So imagine that you apply an electric field to this metallic sphere, a static field. Then it's a force on the charges. So the electrons are attracted towards the opposite of the field. All the electrons move together. So they leave behind them a lack of electrons. So you have the positive charges of the due to the ions. And imagine that you stop. You suppress, at time t equals 0, you suppress your electric field. So that's your initial situation. There is no more applied external field. All the electrons which are here will be repulsed by these negative charges, attracted by the positive charges. All of them. So all of them will start moving. And when they arrive in the region where there are no more surface charges, they have gained momentum. So they keep going. And the story starts again. So it's a swing. Okay, and then you have a frequency of, which is the natural frequency of your material. It depends only on density. And that happens to be in the optical regime. So it's obviously a mechanical oscillator. It's a swing. You have electrons with mass oscillating. But as they do that, obviously, because they carry charge, they generate an electromagnetic field. So it's an electromechanical oscillator, which is in the optical frequencies. And I told you that that particle has a volume which is 5, 10 nanometers. So it's extremely sub-wavelength. So this is an optical resonator, which is extremely confined. And on top of that, if you look at the radiation of this guy, it's not a single electron oscillating at optical frequency. It's thousands of electrons oscillating. So your oscillator strength is huge. So this guy is an antenna. So if you have a large field and a huge oscillator strength, then you can do a lot of things to tailor light emission. So that's the equations to put in a more quantitative way exactly what I told you. You can imagine different shapes. So that would be a thin metallic foil. That would be metallic half space, vacuum here and metal here, or a nanoparticle. Let's take a look at this example, a thin metallic foil. You write the dynamical Newton equation for an electron, and that's the electric field due to these charges. This is electrostatics. This is an undergrad exercise to compute what's the electric field due to this surface plane, surface charge plane. You have both of them, so you get this applying Gauss theorem. That gives you this oscillatory equation. And this is the so-called plasma frequency. I'm sure you all solve exercises where plasma frequency were showing up. That's what this number is. It's the natural frequency of the electrons. It depends on a single quantity, which is n, which is the number of electrons per unit volume. So if this is a standard metal, I told you it's near UV or visible. If you consider a gas of electrons in a doped semiconductor, in a highly doped semiconductor, you are in the mid-infrared, typically between 5-10 microns. Okay, so that's our trick to confine light. What's the secret of this confinement as opposed to the standard cavity? The secret is that in the standard cavity, your energy is electrical energy or magnetic energy. And you have an oscillation between electrical and magnetic energy. When you do that, because the magnetic energy is the derivative through Maxwell's equation of the electric field, you have a non-local relationship, and that imposes a minimum volume, which is the diffraction limit. It's another way of thinking about the diffraction limit. So at the end, you end up with this half wavelength. It's what you have in the example of the cavity with a single half wavelength in the stationary wave. Here, you have electric energy, and you have kinetic energy. So you replace the magnetic energy by the kinetic energy of the electron, and you have an oscillation between these two. And that's the secret of the localized energy. Yes?
Just a quick question. Here, when you show this on the previous slide, it doesn't depend on the geometry of...
It does. Here, I've taken this example. So that's an excellent question, and I will be showing up. So the frequency here is for that particular system. If I look at that one, there is a single interface. So instead of having two forces, I have only one. So there is a factor of square root of 2. This guy will be square root of 2. So that's actually the bulk plasmon. The bulk plasmon, it has this frequency. The surface plasmon will have this divided by square root of 2. This guy, it depends on the frequency, and then you have a square root of 3 for the sphere. And this is extremely important because, of course, if you have a single frequency, it's not useful. But it turns out that you can engineer by applying many, many tricks, and you can adjust the frequency to whatever you want by changing the shape. But you could add a dielectric here, so you would screen these charges, so you would decrease the frequency, and so on. There are many tricks that enables you to play with that. That's why it's useful. Yeah, and obviously you knew that because there is an extremely simple example where you have an electromagnetic oscillator that stores energy in an extremely small volume. It's the hydrogen atom. Hydrogen atom is also kinetic energy of a single electron and Coulomb energy. We don't tend to think of it as light because it's, of course, totally non-retarded given the small distance, but it's an electromagnetic interaction. It's an electromagnetic field at optical frequencies. So that's a bulk plasmon. This is just to give you a very simple and intuitive picture of what is this plasmon. So what I'm showing here is just a gas, an electron gas. And I have introduced a periodic oscillation. So think of a density wave. So it's an acoustic wave, a density wave in the electron gas. And here you have plenty of electrons and plenty of electrons here, and there is a lack of electrons in these bright regions. So because those particles are charged, as opposed to an acoustic wave in water or air, then you also have an electric field. And here you have a large number of electrons. Here you have a large number of positive charges. So you have a field which is linear. So you see that your acoustic wave propagates this way, and the field is longitudinal here. So this is totally different from what you know in vacuum, where the electromagnetic field is transverse. Here it's linear. It's longitudinal, and it's obvious that it's longitudinal. The picture is very simple. It's essentially an electrostatic field that is in the framework of the acoustic wave. And here you see that you have a coupling between the mechanical acoustic wave and the electromagnetic wave. Now we can look for surface waves. Those are transverse as opposed to the previous one, which is longitudinal. So the transverse wave means that you look for a solution such that divergence of electric field is 0. We look for an exponential wave above and below in both medium. And so that's the wave vector. So that would be the propagation wave vector along x, along the interface. And I use the notation gamma for the z component. And of course, if I want to have a surface wave, this should be a decaying wave. So this gamma has to be complex, so that there is a decay. Same thing here. Now, of course, kx squared plus gamma squared is omega squared over c squared times the permittivity of this medium. So epsilon 1 would be 1 if this is vacuum. And what's the condition for this guy to be imaginary so that we have a surface wave? Kx has to be larger than omega over c. So this is an evanescent wave. So this is one of the concepts that we use all the time in near field optics. If when I said evanescent wave, you think of a wave coming into a metal being reflected and part of the wave decays. Sometimes this is called evanescent. You may have heard of evanescent waves in total internal reflection. So those are very specific cases that may induce the false idea that it's related to the material somehow. Here I'm just saying that in vacuum, any wave that has a large wave vector is evanescent. Now, if you take now a point-like dipole, which produces a field, you all know that the field of the dipole diverges as 1 over r cubed plus 1 over r squared, and there are terms like 1 over r. So all these fields, when you Fourier transform them, you necessarily have large wave vectors. So there is always attached to your charge evanescent waves. So the evanescent waves are just the counterpart of this 1 over r squared terms in direct space. If you go to Fourier space, you have evanescent waves. Okay, it's just the same. And of course, that means that you have extremely high confined fields. Large wave vectors are needed to confine the field to small values. A useful representation is the light cone. So in this kx, ky plane, all the wave vectors which are below inside this circle whose radius is omega over c are propagating. For large wave vectors, it's evanescent waves. Another representation that we will be using is for dispersion relations. We have omega, we have k. So this is the light cone. Here you see in 3D the cone. So inside the light cone it's propagating, and outside it's evanescent. Okay, so this is just standard notations. So this is the dispersion relation now of the surface plasmon. Here is the dispersion relation. And you see that it's close to the light cone. It's always on the right side, outside the light cone, otherwise it wouldn't be a surface wave. So it has to be larger outside the cone to be evanescent. So it's always evanescent. This is not at all a surface plasmon. So sometimes it shows up, but it's not. That's your dispersion relation. And the key point here, you see it, that for that frequency, you find extremely large values of k, which means that you can confine the field to extremely small volumes. So that's the specificity of the surface plasmon to confine light, the presence of high wave vectors. Something that is going to be very important for us, it's that you can use these plasmons to tune the absorption. And this is an experiment in 676. It was predicted by Daniel Mestre. The experiment was done by Mike Hutley. And Daniel Mestre numerically predicted back a long time ago that a grading, which is a sinusoidal grading, with a slope which is a few %. So that's a mirror. That's a gold mirror. And the slope is a few %. It's extremely shallow grading. when you shine light with the proper angle, you have total absorption. You see that the reflection factor is 0. So this is the reflectivity, and you see that the reflection factor goes to 0. And so this is clearly resonant. You see the angles, it has a few degree of angular widths. And there is a perfect agreement with experiments. So it is possible to design totally absorbing. So you take a mirror, it's essentially a mirror, and it becomes totally absorbing for a given frequency. So let me show you a plasmon. So let me first, so there's a movie. Let me first explain what you're going to see. So in the camera, the camera here is recording the image of the field along this, which is a thin metallic film. By thin, I mean smaller than the skin depth, so that the light can go through. So it's typically 15 nanometers thickness. We have an optical fiber, and the optical fiber is coated in such a way that there is a tiny hole at the edge, which is what you see here. And this tiny hole emits light. By tiny, I mean sub-wavelength. So if you make a scan of the field, it's 0, 0, 0. Here it takes a value just below that dot, and then it's 0. And because the dot is smaller than the wavelength, if you make the Fourier analysis, you get wave vectors which are larger than 2 pi over lambda. So dot produces evanescent waves. So there are plenty of evanescent waves which are here decaying away from this guy. So when the guy is away, you just see a dot. Only the propagating waves reach the camera. But as the tip approaches the surface, then this surface is illuminated by the evanescent waves. They can excite the plasmons. The plasmons are launched, they propagate. They are being diffracted, they coupled through, some of them are propagating in this side because this is glass. This is vacuum, but this is glass. So some of the waves are propagating in glass. You collect them and you image them. So now you will see a plasma. So the tip was approaching. You've seen the intensity increase exponentially as it was approaching because the coupling of these evanescent waves was increasing. And then you see that the light does propagate over the plane. And it even propagates up to this point where there are stripes which are on the surface. So they scatter the light. So these guys here are illuminated by the plasma and then become again propagating waves, and you can image them. Okay. So those are surface plasmons propagating. Now, localized plasmons. So there is a whole variety of particles that you can design. So all these things, chemists know how to synthesize them. They are absolutely monocrystalline, and the geometry is perfect. So the enhancements are amazing. One of the important things is to understand how light is collected. So they are resonant. If you illuminate these particles on resonance, they have an absorption cross-section, which is like any dipole. This is universal. The absorption cross-section of a dipole is lambda squared divided by 2, roughly speaking. It's 3 lambda squared over 8 pi for the absorption cross-section, 8 pi also 3 lambda square over 8 pi for the scattering cross-section. So when in the extinction cross-section, which is the sum, it's 3 lambda square over 4 pi. For an atom, a single atom, it's 3 lambda square over 2 pi. So this is a universal thing. The difference between the atom and this guy is that here we have losses. There are no internal losses in atoms. The absorption cross-section is the fact that all the light, you see this line here, so those are the pointing vector lines. So you see that this line here goes and is absorbed by the particle. So you see that the effective area of this particle is actually this disk here. And that's exactly what is the absorption cross-section. So keep in mind that when you have a tiny particle that could be 10 nanometer, it will behave as an opaque disk that is typically 300 nanometers, 400 nanometers big. So this is to show that you can tailor the absorption cross-section, so this resonance frequency. So all those guys are nanorods with different sizes, different shapes. So this is the ratio between the aspect ratio. This is gold. And you see that gold has many different colors. You can tune these frequencies. So of course, it depends on the resonance of the particle, which depends on the geometry and also on the surrounding, as I said, of the dielectric material. That's an example of how it looks, the mode on the triangle. Again, this is those are experiments, and these triangles are perfect. They are synthesized by chemists. And that gives you a hint of why we can locally enhance the field. First thing I told you, how do we confine fields? So here you have a mode which is this plasmonic mode. So you have all the electrons going back and forth. And you have different structures of the modes at different energies. And here you see that for explaining the enhancement of the field, not only do you need this idea of resonant excitation of the plasmon, but on top of that, you clearly have a lighting rod effect close to the apex. Okay, so this is a pure electrostatic effect, and you have a huge electromagnetic field here. So this enhancement will be very useful when we will be trying to couple these structures that we will use as antennas to emitters that we will put here, so that the electromagnetic field of the mode is huge. So that's the concept of antenna, using these localized structures to try to control. So that's the concept. When you have a wire, it does radiate, but very poorly. If you connect this coax wire to this structure that you call antenna, then you can extract the light and have a good radiation. The idea is, could you have an atom and bring it close to a metallic structure in such a way that you can do the same thing? And the idea is, can you extract more light? So you have an atom, it has a given dipole. The dipole is fixed. Can you extract more light out of it? And the answer is yes. It does depend on the environment. That's an example of antenna. And the question is, can you extract more sound? So if you have this string, and without the guitar, you hardly hear any sound. When you have the guitar, you do. And how does it work? You have a vibration on the string, which is transmitted to the membrane, the wood membrane, through here, this bridge. So this is a near-field coupling. And then this transmission through near-field coupling, which is very efficient, goes into the membrane. The membrane is very large, and then it's well coupled to the acoustic waves, the mode in vacuum. Those are examples of microcavities. So this was an acoustic cavity. Those are cavities for optics. Those are structures which are periodic, and you have a defect here. Whenever you have a defect in a periodic structure, you have a localized mode, and if you put an emitter here, it will couple to this localized mode. That's another example. Here you have just a nanorode, and you have an emitter in the middle. So that brings me to how can we quantitatively assess how efficient it is to couple an emitter to some structure. And this is known as Purcell factor. It's a classical concept. It's always introduced in quantum optics books, in cavity electrodynamics books, but it's a quantum concept. So it works for your cell phone. The question, there are two questions. You could say that the Purcell factor tells you by how much you increase the emitted power. You can also say that by how much you reduce the lifetime of your emitter. You have a fixed energy. If you increase the rate of losses, relative losses, you decrease the lifetime. So this is often in how we think of Purcell factor, by how much I increase the emission rate. There is another concept, which is, if you think of a cavity, Fabry-Perot cavity, and you have an emitter, it could emit into this vacuum mode, but it can also emit in that particular mode, which is the Fabry-Perot mode. And the Purcell factor tells you what's the probability that it will emit in the cavity mode. And if you can do that, it's very nice, because you can make sure that light doesn't go everywhere, but goes to one mode where you can use it. Okay, so that's this Purcell factor tells you all those things. So you have different way. So what is the Purcell factor? How do you compute that? The idea is that, so this is the very, very simplest approach. You consider that you have a single mode, like I've drawn here, a single Fabry-Perot mode. So the number of modes is 1, but this is not what is needed when you want to know if an emitter couples to the mode. If you want to know that, you apply the Fermi-Golden rule, and the Fermi-Golden rule tells you that the rate of emission is proportional to the density of modes. So what matters is not how many modes you have, but how many modes you have per unit volume, and how many modes you have per frequency interval. So the idea of the cavity is that you have one mode in the cavity, but then you make the volume small, same idea as before, and you reduce the interval of frequency, so the spectral width of your cavity. And by doing that, even though you have a single mode, you can have a tremendously large density of states, number of modes per volume and per unit frequency. So if you assume that your mode has a Lorentzian shape, then you can write that your density of wave is given by that, evaluated at resonance, and of course you divide by the volume. That would be the density of states in vacuum. So this is the standard usual result. So if you make the ratio of these two, you have the probability of being emitted into that mode as compared to all the other modes. And that's what you find. You find this Purcell factor, which apart from a numerical factor, is lambda cube divided by V. So you see that if your V is smaller than lambda cube, then you increase the probability of taking this light, capturing the light. And it depends on the quality factor. Now, in quantum electrodynamics, people have been using high quality factors and volumes which are on the order of lambda or slightly larger. In nanophotonics, this volume could be lambda divided by 10 or lambda divided by 100. So that could be 1 million. We have pico cavities. So picometer compared to tens of nanometers, this can be absolutely huge. The quality factor is poor, because if you use plasmons, you have losses. So this quality factor can be 2 or 3 for plasmonics devices, but this can be millions. So it's a different approach. Okay, so that's about the end here. That's the last thing I wanted to tell you. So that's an example of using a plasmonic nanoparticle. So this is a gold nanosphere, which is glued on an optical fiber. And then you approach, this is attached to an atomic force microscope. You approach it to single molecules, which are on this cover slip. And when you scan this antenna, so it will behave as an antenna. So now you understood that what's happening is, like for the guitar, you have a near field coupling from the emitters to the resonator. This resonator has thousands of electrons, so it's very efficient to radiate. And by doing that, you can enhance the fluorescence. So this is this distance between the two. You look at the fluorescence by organic molecules, and as you approach the tip, you increase the signal. And then something happens. It decreases. So this is known as quenching. What happens is that you have a dipole here, and when it's really close to the gold, so here I replace the sphere by a plane. So if the distance between the molecule and the sphere is much smaller than the radius, it's locally this situation. You have a plane, a tangent plane. And you see what happens. You know that the dipole is emitting a field that goes like 1 over r cubed. So the dissipated power goes like the square, 1 over r6. So this is extremely small. This field penetrates in the metal, and you have Joule effect. So it's direct coupling between the atom or the molecule and the electrons in the metal. And this coupling is extremely efficient, and everything goes into the electrons and nothing is radiated. So you have suppressed the emission because now there is a competing mechanism which is faster, so it takes all the energy, so you have quenched the emission. So you need to be careful not to be too close to avoid these losses. Another last example of antennas, and with that I introduced this key concept, which is you understood that thanks to the Purcell factor, we make sure that the emitter doesn't emit photons but excite the plasmon. And then you can tailor the plasmon in order to control all the properties of the emission. So this is an example where instead of having a single nanoparticles, we have an array of nanoparticles. And the idea is to mimic these things. You know that these things are on the roofs. And if it's too windy, you don't get any more signal because they are directive. The purpose of these antennas is to be aiming in the direction of the antenna, which is emitting. So they are directional. So here we did the same thing. So they are directional because there are interferences between this guy along this direction. So in this paper, they did the same. So the emitters, which are quantum dots, I will explain later what are quantum dots. For the time being, quantum dots are artificial atoms. So these emitters are here. They excite this nanorode, plasmonic nanorode. And then because of multiple scattering, there is directivity in this direction. So this is the measurement of the emission for a single quantum dot. So it's isotropic, as you would expect. A single quantum dot connected to a single nanorode. So this nanorode behaves as a dipole like that. So a dipole which is like that radiates in this direction, this one. So that's what you get. The dipole does not radiate along its axis. So indeed, this is what you see. So that shows that, yes, the emission is mediated by the antenna. You have suppressed the isotropic emission of the atom, and now the pattern is the pattern of this nanorode. And if you add the other ones, you suppress this one and you enhance the forward emission. So the idea is that you can tailor the emission pattern of the emitter by tailoring the emission pattern of the antenna. Okay, are there any questions? Yes? So the quantum dot has different levels. So it depends on which type of quantum dot you are talking about. In what I'm going to, so there could be preferential polarizations. And yes, it would matter, of course, because you need to align the dipole to the electric field. The electric field of the nanorode is polarized along the axis. And this is for a very simple reason. It's always electrostatic. So it's just lightning rod effect. So the Coulomb field is always normal to the surface. Now, in what I'm going to discuss now, in light-emitting metasurfaces, there will be millions of quantum dots randomly oriented, so it becomes isotropic. Other questions? Yes? The loss, you said it?
How robust is it to on which of the gold things is quantum dot located? We show that it is located on the second one from the left, but we put the quantum dots instead on the rightmost.
Ah, no, okay. When you have a wire, so it's called Yagi-Wood antenna. The Yagi-Wood antenna, when you have these things, the real one, the coax wire is coming to that one. And it's been designing in such a way that this is the active source. So that's what we do. We put a quantum dot only close to that one. And this is done by lithography. So you pattern a hole, you deposit your quantum dots, and you make sure that they are there. Now, there is still a question, which is to what extent, so this is your nanorode, and you understood that the fields are varying extremely rapidly here, so whether your quantum dot is here or here does matter. So the strength of the coupling does matter, and this is very difficult to do it reproducibly. Okay, so light-emitting metasurfaces. So I told you that story already. So what are metasurfaces? So that's an example of a metasurface which has been designed to steer a beam. So we want to control the direction. So we come with an incident beam which is coherent. It will be scattered by a metasurface, which is, what is a metasurface? It's usually in nanophotonics, we refer to metasurfaces as a periodic array of resonators. You could break the periodicity. And these resonators will scattered with different phases. So the idea is that they are not identical, these guys. They will scatter the light with a different phase. And if the phase difference between these guys varies linearly with the position, then you tilt your phase and you get this shape. If you can control that, you can control the direction of scattering. How can you do that? Well, for instance, you could have different resonators whose resonance frequency varies. Because you have a resonance, when omega crosses the resonance, it changes sign. So you have a pi difference in phase. And because you have an imaginary part, this is progressive. So just by controlling the detuning here, you have whatever phase you want between 0 and pi. So by controlling these dephasings, you can generate, you can control your phase. Now, you could think, well, those are tiny nanoparticles. What happened with the ray that goes in between? And the answer, I already gave you the answer. You cannot think in terms of rays. And with that picture, you immediately understand that, yes, this discrete area of particles is fully covering the surface, the metasurface. Yes?
So then, if you bring them close enough together so there isn't a gap, then when they start coupling to each other in a way that's more complicated than just their behavior on their own.
Yeah, that's a very good point. And you are pinpointing a key assumption in these metasurfaces, which is that they are independent. And this is, in what I'm going to do, they will not be independent. But in what people do, they are independent. And you need to do that, of course, to make sure that you control the things. If they are not independent, then they are interacting, then the modes are delocalized, and that is going to play a fundamental role in everything I'm going to tell you. So now the key question is, how can you manage to do something similar instead of having a laser beam, your job is to produce light. So you have quantum dots, billions of quantum dots, all incoherent, you excite them, it's spontaneous emission. And of course, this guy is going to be illuminated mainly by these quantum dots, and this guy is going to be illuminated by these quantum dots. And of course, there is no phase relations between them, so it doesn't work. So forget about the standard way of emission. I'm going to discuss two types of emission. These quantum dots, so this is you can excite them usually either by photons, so photoluminescence, or electrically, electroluminescence. You could also have any material here and heat, and that would be incandescence. So this is what I'm going to discuss first, incandescent metasurfaces. Okay, so I want to tailor emission by incandescent metasurfaces. I want to revisit incandescence. So this has been banned from the European market many years ago because they are bad, and they're bad for very number of reasons. Emission is isotropic, it has a broad spectrum, you cannot turn on and off very fast, so you can use them. You cannot use them to transfer information. Efficiency is very bad, and the brightness, so the number of photons in each mode, is very low. So the question is, what of this that we all took for granted always? What among these properties are fundamental, imposed by the physics, and which ones are just due to the fact that we're not working properly? The only one that is fundamental is this one. The low brightness is given by Fermi-Dirac. If you have this is incandescence, so it depends on temperature. Number of photons at a given temperature is given by Bose-Einstein distribution, period. So there is no way you can put more photons in a mode. All the rest, I'm going to show you that we can manage and do it. So this is what I'm going to show you now. So this is an example of grating. It's made of silicon carbide. We hit that surface. So there is no, we do not scatter, we do not shine light on this. It's just there. We increase its temperature by heating, and we look at its emission in the infrared. This is at 11 micron, and this is what you see. So it looks like a radar pattern. It's highly directional. So this is a proof of spatial coherence. I'm going to discuss later why I'm saying that it's one and the same directionality and spatial coherence. This is a proof of spatial coherence. So you can have a thermal source which is directional. I'm going to explain later on how we deal with that and how we can understand that. How could you design this? And actually, this is the reason we did this experiment first. There is something which is called Kirchhoff law that goes back to Kirchhoff, 1817. That tells you that the emitted power when you hit a body is given by this law. So this is the optical étendue. That's your radiance or specific intensity. And it's given by the radiance of the black body at equilibrium, which depends on temperature and wavelength. And there is a factor which is the emissivity. So that factor contains all the information about whether your material is a good emitter or bad emitter, how it depends on the angle. Now, Kirchhoff proved that this emissivity is equal to the absorptivity. And that's, if you think, it's very striking. It's because that is, belongs to usually thermodynamics classes or radiometry world. And this is really coherent optics. Absorptivity, you take a structure, you shine a plane wave on it, and you compute the absorption. So that's the bridge between two different worlds. And we can design whatever metasurface we want, computing with standard Maxwell solvers this absorptivity, and then we hit the thing and it works. So that's kind of magic. So it's really worth trying to think about it and understand where it's coming from. The proof of Kirchhoff, of course, was based on ray optics, because this is what he had at that time. In this paper, we did the derivation based on Maxwell's equation, so which is much more general. It's valid in the near field, in the far field, and it takes all the coherence effects in account. But it is valid, that's the point. Silicon carbide has a surface wave, so I've been explaining what are surface plasmons. You have the similar surface wave on silicon carbide. It's not a metal, it's not a surface plasmon, it's a surface phonon polariton. But it's exactly the same structure. You have the same type of surface wave. And I showed you that this gold grating could absorb everything. Same happens here. So we design a grating that can absorb 100%. And this is how we design this guy. And that's why it emits like that. We had a dispersion relation. So if you have one frequency, you have one angle. For one frequency, you have one angle. So that's exactly this peak. This peak is the same as the total absorption peak before. Kirchhoff law tells you if it absorbs, it emits. Since it absorbs resonantly for a given frequency and a given angle, it emits in a given frequency, a given angle. So that's the trick. So the trick is really due to the fact that you have a plasmon. Let me try to give you now some hint on what's the physics behind this Kirchhoff law and what's a physical image of what is thermal radiation. So you have a piece of material, it has temperature T, and think of metal, you have electrons, they have random thermal motion. If it's a crystal like silicon carbide, you have these atoms of silicon on carbide which are moving randomly because of the phonons, which are thermally activated, and they do carry charges because they do not have the same electronegativity, the silicon and carbon. So you have random dipoles. So what I'm telling you is that at temperature T, each volume element is a random dipole. So random dipoles, it's time dependent, so it radiates light, classically. The average is 0 of the current, so the average of the field emitted is 0. But we don't measure that. We measure the flux of the Poynting vector, which is quadratic. The electric field is, of course, linearly related to the current because Maxwell's equations are linear. So whatever the field emitted by all these random dipoles, the field here is linearly related to this current, and that this is called Green's tensor, and it's simply the field radiated by a dipole. So the field at R radiated by a dipole at R prime. And you need to integrate over all the volume. If you take the square modulus, you see immediately that what is needed is the average value of the correlation function of the currents. And the question is, do we know that? And the answer is yes. This is called fluctuation dissipation theorem in statistical physics. And this fluctuation dissipation theorem tells you that this correlation function, wow, here we have Planck's function. And here we have the losses. To emit, we need absorption. Emission is proportional to absorption. Imaginary part of epsilon is the local absorptivity, and that's Planck's function. So with that, you prove this. You can prove this thing. This is, I'm sure you never heard of that because it's no longer taught in classes. But you see that Lorentz did that in 1916. Problem is that in 1916, the fluctuation dissipation was not known. The fluctuation dissipation theorem. So the correlation of GG was classically the correlation of VV, so V squared is KBT over M. So that was a failure to explain Planck's function. So it's got forgotten, but then later in the 60s, Ritov in Russia developed this formalism that we call fluctuational electrodynamics, where you take Maxwell's equation and you put this random current as a source. But when you do that, you can compute the field radiated by a current in any structure, any antenna. This is just a standard Maxwell question. We can do that. And then we benefit from all these resonances of the material. And it's very simple. Now, that's what we do. We solve Maxwell's equation with solvers. But let me give you a hint of what's going on and where this Kirchhoff law is coming from. Because the paper I've shown you, it's kind of technical. So let me give you a hint of why it works. So that's why I'm telling you Kirchhoff law is emission is equal to reflection. That's just a sheet of paper with black ink. So the black ink means that here the reflection is 0, and therefore everything is transmitted, so it absorbs and you have a large emission. Now, I'm cheating when I'm showing you because this emission is with an infrared camera and this one is a visible picture. And of course, the equality hands for one wavelength. But it turns out that I'm not cheating that much because it is indeed a black paint also in the infrared. So let me explain in 1 minute how it works, this equality between absorptivity and emissivity. So we think of an incident beam coming on this interface. This is a half space. I'm assuming that it's an absorbing medium, and I'm assuming that the thickness here is large enough so that there is no transmitted field. So it's either reflected, the energy, or transmitted. Once it's transmitted by the interface, it's an interface transmission. The photons are inside the material. They will be absorbed. So the transmission factor of the interface is the absorption. Now, if we look at the light emitted, where it's coming from, what I discussed before, well, I'm telling you that there are plenty of electrons, ions, moving, random movement. They emit photons. Even in the medium is absorbing, it's opaque. There are photons which are emitted, and they are reabsorbed very soon, but they are still emitted. So here, if you say that this has a temperature T, then the moment you say there is a temperature T, you are saying this is a local thermodynamic equilibrium at temperature T. So you do have a black body radiation at temperature T here, and these photons are either reflected or transmitted. And once they have been transmitted, you call them emitted. And there is reciprocity, which tells you that if that's a source and that's a detector, and you look at the signal that you get here, if you do that, you get the same signal. That's a reciprocity theorem. And as a consequence, T12 is equal to T21. So T12 equal T21. So alpha equal epsilon. So Kirchhoff law is really due to reciprocity, and also, if you look in detail, reciprocity of the matrix element for absorption and emission, it's the same. So with that, I hope I've convinced you that if I can tailor the transmission, I can tailor the emission. So everything is about designing a particular transmission factor. So my grading was a surface whose transmission factor was essentially 0 everywhere except in one particular direction where it was 1 for one particular frequency. So that's what we need to do, to design structures that aim at controlling the transmission factor. Now, in terms of surface waves, what's the origin of the coherence? So I gave you this picture that the light emitted is due to the emission, electron-hole recombination, if you want, or excitation, emission due to random dipoles here in this volume element. Because of this Purcell factor story, you get the picture that most of the emission will go into this localized surface plasma instead of other modes. This localized surface plasma, not localized, the propagating surface plasma. The propagating surface plasma propagates along the surface. It's scattered by this grading. And since at a given frequency it corresponds to a given wave vector, that's grading low. For a given wave vector, you shift it by 2 pi over d, where d is the period of the grading, and you get a well-defined direction. And you see that the field is coherent because if you look at the field here and here and here and here, it's partly due to this same plasmon that has been generated here. So the coherence of the field along the surface is due to the fact that we have excited this delocalized mode. And that's coming back to your question. The key for the coherence is that we have excited a delocalized mode, and because delocalized, when I excite here, I control the phase, I generate coherence of the field at every point. That's the key. So we need to work in exactly the opposite regimes that what people have been done. That's the key. So we understood that from there, and now we will be applying to design coherent sources. Okay, temporal coherence. That's a different story. So we want to do emitters which emit a given peak instead of this broad thing. How do we do that? Well, the idea is you start with a mirror, so that's gold. You have a mirror, so it reflects everything. It doesn't absorb anything. And then you want to generate some structures that will absorb at a particular frequency. So you put local absorbers. And here, for instance, you have a disk. And this disk has a plasmon, which is here. And this plasmon will propagate like that. And it will be reflected at the edges. So that's a Fabry-Perot for a plasmon. So by controlling these widths, you control the resonance frequency. You have a large field here. This is lossy, so you have losses at the frequency that you have chosen by design. You can play the same thing, same trick here, and you see that you can, modifying the lens, you have 2 peaks. And look at that, 100%, almost 100% absorption. So you see that this naive picture of geometrical optics, the ray that falls here would be absorbed at a given frequency, and another ray at a different frequency will be absorbed here. You would expect, if you think in these terms of ray, 50% absorption maximum, but you do have almost 100% absorption for all of them because they are capturing the energy because of the cross-section. This is interesting. Here you have a hot piece of material, and to control the temporal coherence, you just build right on top of it a filter. So you have a multi-layer structure. It's a standard filter. And by doing that, you manage to control the transmission factor, just like you do with dichroic systems, multi-layer systems. And you can tailor your spectral emission. Well, there are other resonance systems. Let me skip that for the sake of time. Okay, that's a technical point. I want to, so far, I've been telling you, if it's monochromatic, what I just did, then it's temporally coherent. And before I told you if it's directional, it's spatially coherent. So I want to justify this statement and tell you why I'm saying that. So we start with the first, which is very well known. If you look at the time correlation function, so to address the question of coherence, coherence is just a fancy word for optics people, but it's nothing but a correlation function, a standard correlation function, nothing more. And you ask the question, my field is random because my sources are random, because it's spontaneous emission, so it's a random process. So I'm interested in knowing if the field at the position R1 and the time t tau is correlated with the field at a different point and different time. So here we look at the time correlation, so it depends on tau, which is the difference in times. And there's this well-known Wiener-Khinchin theorem that tells you that this is the Fourier transform of this, which is the power spectral density. In that particular case, because we are looking at two different points, it's called cross-spectral density, but that's a detail. This is the definition of power spectral density. So that tells you that if it's monochromatic, it's a Fourier transform. So if it's monochromatic, then the Fourier transform is very broad. So you have a long-range coherence. So for large tau, you still have correlation. If that would be extremely broad, then delta omega delta t is more or less 2 pi. So if it's broad in frequency, then delta t is small, and then you don't have a good time correlation. Okay, this is just a Fourier transform property. That's coherence for fields. This is not what is used in quantum optics. Now, this one is much, much less known. Whenever you talk about far-field spatial coherence in all the books, you end up with Zernike-Van Sittert theorem. But this is not what is of interest here. What is of interest is this formula, but for spatial variables. So you look at the correlation function of the field at 2 points in frequency domain. So get rid of this temporal coherence. And of course, that's a correlation function at 2 points. So it's the same function, the same Wiener-Khinchin theorem. And you, instead of having omega, you have the conjugated variables in the sense of Fourier transform of R, which is K. Here it was temporally coherent if it was monochromatic. So here you want to have it mono K. So a few wave vectors, so directional. So that's, strictly speaking, the Wiener-Khinchin theorem for space variables. And that tells you that if spatial coherence and directivity is one and the same. Okay? That spatial coherence is in the source plane. Okay, so this was just to explain. I have 15 minutes left. So I wanted to discuss efficient incandescent sources. Let me just make it very brief for the sake of time. The key message is that there is nothing fundamental that tells you that an incandescent source should not be highly efficient. So let me explain why. If you have a hot membrane like that, you heat it, it will emit light. It will be cooled down by convection through the air. So you put this in vacuum and you suppress that. Then you will have losses due to conduction. So if you take a membrane which looks like that, you reduce the contact points and it's isolated, you can manage the fact that the conduction losses will be reduced, and this is what people do for bolometers, and you can have a very good insulation. It's really an engineering design issue, but it can be done. You can heat only the central parts so that this cools down, and therefore you recover the emission. So if you manage to suppress conduction and convection, what you need to do to increase the efficiency is to make sure that unwanted radiation, meaning grazing incidence or some frequency that is not of interest, is suppressed. So you can do this by designing metasurfaces to make it directional and monochromatic. And if you do that, basically you manage to improve your efficiency. So the next question is why people don't do that for the light bulbs. And the answer is everything I told you was in the infrared, where I'm going to heat to 1000 Kelvin, and to put it in vacuum is not an issue. If you want visible light with incandescence, you have to heat up to 3000 K. 3000 K, you start vaporizing your emitter. And then you need to have a gas and play very astute and beautiful tricks so that there are chemistry where the vaporized tungsten is redeposited on the wire, and you need a gas for that. But if you are at 1000 Kelvin, you are not vaporizing your emitting material, so it's not a problem. And this is an important issue because there is a lack of cheap and robust emitters in the infrared. Okay, so let me skip that. So that's exactly what we wanted to do here, to design a metasurface that is going to be directional and monochromatic. So here, this is our goal, our target. We wanted as a function of angle to emit in 20 degrees. We cut here, and the frequency here is 4.26 micrometer, which is the absorption frequency of CO2. So we want to make an infrared emitter for detection of CO2 in a room like this one. So we can do that by designing this type of metasurface. And here, because we have, let me show you. So this is a metal, and now this is a local resonator, as I've explained before, but it's coupled, so they are not independent, they are coupled. And you see that we do have modes, as you can see here. You see the dispersion relation, so those are really modes propagating over the interface. And so you need to design this thing. You understood that the design is using numerical Maxwell solvers to optimize the absorption. So we design these structures in such a way that the absorption is maximum here. There is a trick on the mechanism that makes sure, but roughly speaking, you see that in this first part of the Brillouin zone, you have a strong emission. There is a condition for having a good absorption, which is the so-called critical coupling. I will mention that later on. That's another type of metasurface, which is enabling to control the emission. So again, we control both the emission spectrum and the direction. So this is made of dielectric non-absorbing resonators. This was designed by Cédric, who is here in the room. It was a collaboration with the group of Xavier Letartre at INL in Lyon. So this resonator is really here to enhance the field. The absorption takes place in the platinum. So by controlling the distance here through silica of silicon, you have a large field. The tail of this field will produce its losses in platinum. So the amount of losses is controlled by controlling this. The radiative losses are controlled by breaking the symmetry. If this grading, if all the cylinders are identical, then there is no emission, there is no coupling. So by breaking the symmetry, you change the period. So by having this guy is smaller than this one, you break the symmetry, so you fold your Brillouin zone, and you bring back a surface mode into the first Brillouin zone, so in the optical cone, and then you can excite it. So by controlling the radius difference, you control the radiation losses, and it's a beautiful system because you can control all different parameters of the metasurface separately. You see that the measurements here are in very good agreement with the numerical simulations, so those things are very well controlled. Okay. Now I shift gears and I address the question of, is it possible to modulate very fast thermal emission? So the trick to modulate thermal emission is, there are two. Either that's your emission. So I want to turn on and off very fast. So there are two ways of doing that. Either I cool down the system, and then I hit, and I cool down, I hit. But then it takes a long time because cooling is slow. There's another option, which is you keep it hot, and somehow you manage to turn your system into a black paint, mirror, black paint, mirror, black paint, mirror. If you can do that, it emits, it doesn't emit, it emits. So this is what is done here in the group of Professor Noda. So the system consists of quantum wells, which are absorbing layers in semiconductors. There are 63 of them. And by applying a voltage, you can remove all the charges from the quantum wells so that they cannot absorb anymore. And this can be done very fast. So the system goes into this absorption, non-absorption regime. And you see that they managed to control the emission up to 600 kilohertz, which is a remarkable achievement. And the thing was hot all the time, but you can modulate the emissivity, you see, with a depth of modulation, which is remarkable. There are other examples. Let me skip that. And here, this is something we did 5 years ago. We modulate temperature here. So the challenge is it possible to cool down the thing? And the answer is yes, if you have platinum wires, which are very thin. The thickness here is 30 nanometers, and they are deposited on a cold substrate. So now, it's not, there's no such a thing as the temperature of the sample. Only the wires are hot, and we can heat them just by Joule effect, by applying a voltage. When they are hot, we stop heating them, they cool down by conduction. And this conduction is very fast because it's limited by diffusion, and diffusion goes like the distance square, and the distance is very small. So it's here for such a system, the limiting diffusion time is on nanoseconds time scale. So heat transfer is very fast if the things are nanoscale. For the design, we have an issue. I told you that we design everything by controlling the absorption. But we were assuming that the temperature is the same everywhere in the sample. And here we have the wires which are hot, but the substrate is cold. So it doesn't work anymore. So we need to generalize this Kirchhoff law to account for a non-isothermal field. And this can be done, and it's done in this paper. And actually, the idea is quite simple and intuitive. It turns out that when you have a sample, you can define what fraction of the incident beam is absorbed in a given volume. And this local absorption plays the role of a local emission, but then it depends on its local temperature. So we generalize it to a local Kirchhoff law. So that means that when you shine a beam on this structure, part of the light will be absorbed in the metal. That tells you what's the emissivity of the metallic part. You multiply by Planck's function black body radiation at the temperature of the wire. Part will be absorbed here. We multiply by the temperature at this point. And it turns out that most of it is due to the emission of the wires. So this is an example with a 7 microsecond pulse emission. You see that we do have a pulse, we measure a pulse emission. And that's the emission spectrum. I think I don't have time to discuss. This is here, you see that the modulation, this is 10 megahertz. So you see that we're able to go up to 10 megahertz, which is very fast for heat transfer. Very recently, what we did was to try to control emission and produce circular polarization. Thermal emission, we take a sample, we heat, and we want to produce circular polarization. So what we did was to take the same sample, but to introduce some chirality in the wires. And as you would expect, the emission of circular polarization takes place here in these parts of the samples which are producing the chirality. We can look at it by looking at the absorption, and this is absorption for left circularly polarized incident, and this is absorption for right circularly polarized, and you see the decrease. Indeed, there is much more absorption here in this area for one circular polarization. So that's the trick, and it's always Kirchhoff law that enables to design these things. Okay, so let me skip that, I think. So I would like to tell you a few words about photoluminescent metasurfaces. So first of all, thermal emission, electroluminescence, and photoluminescence. How do you know if what you have is thermal emission or luminescence? Regarding emission, if we take the example of semiconductor, you have a valence band and conduction band. Emission is always electron-hole recombination, so it's the same process. So the only difference is how you excite the system. In electroluminescence, you apply a voltage and you inject electrons in the conduction band. Very fast, they thermalize. So the key here is to have in mind that the equilibrium between the electrons in the conduction band is due to electron-electron interaction, and the time scale is hundreds of femtoseconds. The recombination between the conduction band and the valence bands is spontaneous emission, that's nanoseconds. So you have a population at the equilibrium of electrons here, which is given by a Fermi-Dirac distribution, and you have another one here. And they are splitted by an energy which is exactly EV, where V is the applied voltage. But you could produce the same thing by pumping optically. The difference is that for thermal emission, your electrons here are promoted thermally, and it's due to this tail of your Fermi-Dirac distribution here. So the only difference is this presence of this so-called difference. So this is called quasi-Fermi level. The difference between the two quasi-Fermi levels is called photon chemical potential. I'm sure that many of you heard that there is no such a thing as photon chemical potential for photons, because that's the way it's in most of the lectures based on the point of view of Bose are based. So it can be defined, and it's very well controlled. Okay, so that's the sample. That's an example of a sample, an experiment done by in the group of Aloïs de Giron. So the idea is really to do that. You have this metastructure with resonances. You have this array of disk, and you deposit a layer of quantum dots on top of it, and you look at the emission. And Aloïs was very disappointed because looking at different points of the samples, he would get different spectra, and that was a mess. And you see that they grow very differently. So one of them is photoluminescence, the other one is electroluminescence. And by assuming that this formula is valid, then I make the assumption that maybe the temperature was different for these different spectra. So if you introduce a temperature difference between these two and you renormalize using this function, then that's what you get. So you get that your photoluminescence spectrum that was looking different from the other ones fits exactly, and all the different electroluminescence are fitting. So the difference of temperature is on, you see the values, they are not huge differences. This is due essentially to electrical contacts locally that are producing two different. So that means that all these processes of emission by ensembles can be explained by this model. So in this model, the ensemble of quantum dots is accounted for in the absorptivity, and there is an effective refractive index for the ensemble. So we homogenize the ensemble of quantum dots. So the key difference now, so what I'm just told you is that we model photoluminescence and electroluminescence with the same model as incandescence. We only introduce a mu here, which tells you how intense is the excitation. And this mu, in case of electroluminescence, is exactly EV. So that's the standard model for LEDs. But it's been generalized here for metasurfaces. Okay, so what we want to do now is to have an ensemble of nanoplatelets. Nanoplatelets are like that. You see the thickness is 4 nanometers. Here we have 13 and 20 nanometers. So they are very bright. That's a picture of the ensemble of these nanoplatelets, and that's their absorption spectrum. So we want to design a directional source, and we want to make it very efficient. We want to make it very bright. When people do that, they think in terms of nano antennas, the concepts I introduced in the beginning, and they put a dipole in the structure, they look at its emission, They average over all positions. But when you do that, you don't know what's the amplitude of the dipole, so you don't know how good you are doing and whether you are close to a limit. When you use the Kirchhoff law, you know that whenever your absorptivity is close to 1, you cannot do better. So that's what we did. We optimized the absorptivity. So I think I have to skip that part. We reached 60% absorption in the quantum dots, the nanoplatelets. And you see that with the main structure, the thickness is 100 nanometers. To have the same absorption, we need a layer whose thickness is 8 times larger in case of without the metasurface. So the presence of the metasurface is really helping a lot to absorb and therefore to emit. And that's the final result. You see that we manage, by controlling these modes and engineering their losses, to have a highly directional emission. So this is the angle frequency. You see that with the metasurface, we confine the light close to normal incidence, whether it's almost isotropic otherwise. Okay. With that, I'll stop. That's the summary. That's where we've been showing that we can control the polarization, we can control the spectrum, the direction, we can modulate. We can do the same for photoluminescence. Thank you for your attention.